Welcome, everybody. So, my name is Richard Bulger, and I teach on the IT courses in the Open Education Unit. So, the most boring part of IT, I think, is databases. So, I deliberately picked that today to present on. It's something that people take for granted. They know databases exist, but what exactly are databases are a moot point to a lot of people. I did what any good student would do. I went to Wikipedia to have a look to see what it says about databases, and it gave me this nice reply. A database is an organized collection of data generally stored and accessed electronically from a computer system. Where databases are more complex, they are often developed using formal design and modeling techniques, which didn't really shed any light on what a database is at all. And that's pretty typical of Wikipedia. People get very caught up in the detail of it. But if you break it down, databases really are collections of data. And the modern internet, the way we use it today, it wouldn't be very useful at all without databases. Every time you do anything, if you go on Netflix, you're accessing a database. If you go on email, obviously you're on a database. Databases sort of add live, vibrant data to what we have in the internet. Databases, if you break it down, it's all about data. So what exactly do we mean when we say data? Computers work in terms of ones and zeros. Bits, we call these binary digits. Computers then bundle these bits together, and then 4 bits would be called a nibble, and then up from that is a byte. So these are a sort of computer engineers' sense of humor. So nibbles and bytes. Generally, we talk in bits and bytes. We don't really use nibbles anymore. So let's have a look at a bit. It's a 1 or a 0. So with a bit, you can store something like if somebody's guilty or innocent, if something is true or false. It's just either one thing or the other. It's very binary, literally. There's no gray areas when it comes to computers. With a bit more information, we can store a bit more. So if we have 2 bits, that gives us the ability to store 4 bits of information, 4 pieces of information. So if you were to navigate a maze, for example, and I was talking into your ear, I could give you instructions in binary. I could say 0, 0 means up, 0, 1 down, 1, 0 left, and 1, 1 for right. So with 2 bits of information, suddenly now we've got the ability to give a little bit more than just true or false. We can do up, down, left, right. And as we add more and more bits, we can model more of the world. The colors of a rainbow, in school you might have done Richard of York gave battle in vain, or ringing out your great bells in victory. They say there's 7 colors in a rainbow if you look at it. So we'd need to use more bits to store that information. Well, because of 7 colors, if you look at it, 1 bit will give you 1 or 0, 2 will give you 1, 2, 3, or 4. So 3 bits will actually give you 8. So with 3 bits, we can model the colors of a rainbow. I know there's 7 there, but it only works at 1, 2, 4, or 8. So moving up, we can do a lot more. Say if we wanted to encode a book, we'd use some sort of encoding to convert the letters of the alphabet, bits of the English alphabet. But we also have special characters. We might have uppercase and lowercase, for example. That's 52. And then we might have underscore, dashes, dots, emojis, whatever you like. So the way they do it officially is they use 8 bits, and they have something called ASCII. So with ASCII, we can encode all the letters of the alphabet and a bit more. And when a computer, actually, when you type a document, all it does is store these bits on a file, ones and zeros, and they represent the letters that you're typing. We all use Spotify. Again, that's computers organizing audio data. So in the real world, we listen and we hear sounds. They're actually waveforms in the air. The air is pressurized, and we can use a microphone to digitize that. So the blue here is the waveform, and the green is a computer trying to turn those samples into discrete numbers. So you might, first one there, first sample might be 2, then 6. And the more bits we give to digitizing a waveform, the more true to life it sounds. So you get, with 16-bit sampling, you can do CD quality audio. And we sample that 44,000 times a second. 16-bit audio is, if you imagine a stack of paper, it would be about 12 foot high, and it gives you a resolution that it can pick out one particular piece of paper in a stack of 12 feet high. So it's very precise. It's never going to be exactly the same as the waveform it's digitizing, because the real world is analog. It's very fuzzy. But computers like ones and zeros, so we digitize it. So computer purists, if you're into your vinyl, it's a pure analog scenario. They'll always say, "Oh, analog is better than digital." But if you go down to a small enough level and digitize it, the quality is as good as analog, even better sometimes. Moving up, we can also do pictures. We can allocate 8 bits maybe to red, 8 bits to green, and 8 bits to blue. That gives us 24 bits. And that represents a picture element. So a dot on your TV screen might have 24 bits of information behind it. The computer is storing. Moving that out, we go up to something called hex. We have 10 fingers. That's why we have a decimal system. If we were designing a human from scratch, we might give them a few more fingers. It would be really good if we had 8 fingers in each hand. Then we could count in something called hexadecimal. So instead of just 1, 2, 9, we'll have 1, 0, 2, F. And that will give us the ability to really be efficient with our digital encoding. So all ones would be FF for a white pixel. That's red, green, and blue all switched on. If we just wanted to switch on the red pixels, we'd switch on color FF0000. Green would be 00FF00, and blue would be, because it's red, green, blue, it'd be 0000FF. Putting that all together, we can do an image. A typical high-definition screen will have 1980 pixels across and 1024 pixels down. And each of these will have a red, green, and blue component of 8 bits each. So it gives us that number, 49,766,400 bits in each picture that you look at your TV screen. Now that's quite a lot of bits. But we can store that easily, and we can also use stuff like image compression to even compress it down more so that we don't actually have to store bit for bit. But if we're talking raw unencrypted video, we might have 60 of those frames per second. So it's an awful lot of data. Luckily for us, data gets cheaper every year. That wasn't always the case. But if you consider that number, that 49 million bits, that can represent any picture you've ever seen on a TV screen. So with those numbers, we can display family photographs, Casablanca, anything you can think of, any image in high def can be displayed by those bits. So the more bits we have, the better it gets. As I say, storage is key to databases. Storage wasn't always cheap and prevalent. In the 40s, after World War II, they started designing the first true programmable computer. There's a debate between the Americans and the British as to who was first, but I'd give it to Manchester University, where they built this system called the Baby. Up to then, in World War II, they had computing machines that couldn't store their programs in their own memory. So what they did was they used paper tape, and they hardwired the code as such it was into a computing system. But the definition of a computer is that it stores the computer itself in its own memory. And the first one to be able to do that was called a baby. Electronics in those days, we didn't have transistors or chips. We had thermionic valves. And the key to digital information is these valves or switches. And to make a memory would take an awful lot of electricity and space. But one engineer over in Manchester had an idea to store bits on the screen of a CRT. Now, they had a lot of CRT, cathode ray tubes, from television and also from the radar program. So these were quite cheap. So they used the beam, and if you look at the dots on that screen, the program is stored on the screen of a cathode ray tube. There's no RAM, nothing. This is as good as it got. They could do about 2,000 bits on one typical screen. That was enough to write a small program and process information. But if you switched off the tube, you lost all your information. So that's sort of a random access memory, it was called. They needed something more permanent, so they invented these spinning disk drums that they used, would you believe, in the late 1900s. And they modeled them to store, a bit like washing machines. They magnetized the skin of these drums and stored ones and zeros on it. This is a disk from the 50s, so this is 10 years later. This is an IBM disk being shipped off on a truck. It's 5 megabytes in storage. So that's quite a small amount compared to today's. If anybody remembers floppy drives, floppy disks used to be able to store around 1.44 megs. So a hard disk of 5 megs, you could maybe fit one song on it with audio compression, maybe a small image, but not much. But these two concepts between, on the left, the random access memory and then the hard storage, we still use that today in all our computer systems. Instead of B screens, we now use RAM. So we have little sticks of RAM, random access memory, and this one will store, you can get them now, they'll store 16 of data. If you look at it, 8 chips all stuck on here, and each one of these chips stores 1 bit of a byte. So you'll often see this in computer circuits, that you'll have 8 or 16 or 32 bits all stuck together, so that the computer can access 8 bits at a time, or 32 bits or 64 bits. Along with that, we have hard disks have gotten better and better. They're still spinning bits of metal for the most part. There are new SSD drives now, but they're not as cheap, and they're not as good at storing large amounts of data. So we use hard disk. We still have this old Victorian style spinning a metal disk and with an arm across it. You can get that disk there. I looked up, it's the biggest disk you can get at the moment. It's 18 terabytes. With 18 terabytes, you can store every song ever recorded. So that's including 2,000 versions of White Christmas, for example. Storage is cheap. Get that into your mind. If you take anything away from today, storage just gets cheaper and cheaper. This is what a hard disk looks like nowadays. It's every computer you have will have one of these. That's storage. When we want to access this storage on a computer system, there's a waveform that I digitized. It's stereo. We've got 2 channels of audio. We save this file. So it's called sound.wav there. And if we look inside it, we can see that it's just these hexadecimal characters. They represent the levels of the sound. So again, even though it's a sound, the computer will model it as just ones and zeros. So any data we need to model, we use ones and zeros. So we can model the world, we can do audio, video. Very importantly, we can do numbers. We can record bank transactions, which is a big part of the database as we know it. The problem is, how do we manage it? So the first thing they did was they said, oh, computers have files, so we can save files on disks. So let's just make a file. So here's a file on disk here. It's got 4 entries on it. Number 1 is John. Number 2 is Paul. Number 3 is George. Number 4 is Ringo. So with that file, I can look and see if I wanted to see how tall John, these are the Beatles, obviously. So I've just done a small file called beatles.txt. I can go in and look at it. And so the command I use is grep John. And then the file is called beatles.txt. And then I'm using something called a pipe symbol into a cut command. And the -d here says to delimit. So I'm chopping up the file, each line by a comma. And then I'm saying which field I want. I want field number 3, which corresponds to the height. So John Lennon was 179 centimeters high. So that's sort of giving me access to the data, and I can usefully process it. So when you organize data in such a way, it becomes information. It becomes something that we can use to make decisions. So I could write a program here. I could get John, Paul, George, and Ringo's height, and then I can look and see who is the tallest Beatle, for example, who's the smallest, what's the average height. The problem with this is that if somebody else is accessing that file at the same time, then they might update it, or they might delete an entry, or they might corrupt it in some way. For example, if they had fat fingers and they typed 2 commas instead of 1, then this code will crack up and it'll stop working. And this is what happened with the early databases that they built. So we need something else just to order the data a bit more and be more user friendly. And this is where the relational database management system comes into it, the RDBMS. So on the left here, you've got database, which is your ones and zeros, and on the right, you've got your users, and you might have applications, you might have robots or scanners out there that are updating the database. Now, the DBMS, when we talk about databases, really we're talking about DBMSs. They take in different users' requests, they process the data, and they present it in such a way that might be useful for them. So when people say databases, they generally talk about what they really mean is a database management system. And the most common one of them is the relational database. You can build one of these relational databases. It used to be only very large companies could do this, but now with storage cheap, processing power cheap, and open source software, you can build a very powerful system for very little money. And what we typically use is something called a LAMP stack. We take a Linux operating system, we put an Apache web server on it, we use a relational database management system called MySQL, and then we write some code called PHP. Putting it all together, we get something called a LAMP stack, and you'll find most web services are built on LAMP stacks. The reason we use Linux, it's free, open source. 90% of the cloud runs on it. 96% of the 1 million servers, top 1 million servers run Linux. So Linux is your operating system. It's not Windows we use. We don't use Mac OS. It's pure Linux. We use something called Apache, which is, again, it's a free web service. Web server, sorry. It listens on port 80. So it's like a telephone number. You can ring up any machine on the internet and say, are you available for requests on port 80? So when you go to www.rte.ie, you go to a web address and ask on port 80, can you give me some information? Here I'm logging into a web server and I'm typing in the get command, which says, give me your home page, and then it sends back some HTML script. So the key to it all is this MySQL relational database management system. And this is what it looks like. Now, instead of just typing a file, I go create database. I'm going to call it the Beatles. I'm going to use that database. Then we have something called tables. So these are just where we store the information like before with the file. So I'm going to say, I'm going to have a members table, and the first one of these is going to be an identifier. And it's called a primary key. This prevents me having two Johns or two Pauls. You only have one identifier, unique identifier in each member of the band. The next one is called a name, so that's their name, and then we have another one called height. So I can then insert information into this database using the insert command. So insert into members, values, and then I, like before, I now go select. The database is populated. Now I can take information from it. So instead of before I had that long command with grep and pipe and cut, now I can go select. And it's very English sort of language syntax. There's only about 50 commands in it. So this is the SQL, structured query language, they call it. And this is what most relational databases will use. So I can do select everything from members, and it gives me back all the Beatles. I can just select name from members where ID equals 1, or maybe I want to get the height of John like before. So I can go select height from members where name equals John. So it's very, even if you've never studied it, you can look at an SQL command and sort of work out what's going on. Whereas before, to do that with the cut and all that, you'd have to look up what these commands mean and remember them. So SQL is actually quite user-friendly. The last part of this LAMP stack is PHP. So this is a programming language. And in there, we generate this HTML that the web uses. So we interrogate the database with PHP, and we run SQL commands. So in here we have the select everything from members. But then we're also doing a query on, we run that query against a database, and then we serve that up on our web server. So when I run this command, it generates that web page there. So that web page is up there now, live, and I can change the program in any way and render a different web page. So this is how they make interactive dynamic web pages that change. They're not always static, boring, same page every time you go to it. So you might have the news headlines updated, and all in the back end there's a database where some journalist is updating the story. And if you want to see the top 10 stories, you can just write a little script and populate a web page from it. So this is why databases sort of are the key to making an interactive dynamic internet that we have today, not like in the early 90s when we just wrote static HTML pages.